Welcome to the deep dive. Today we're venturing into a really fascinating area, task-agnostic systems.
Mhm.
You shared some great material with us. And, well, our goal is to unpack what these systems are really all about, why they're becoming so important, and maybe, peek into where they might be taking us.
Sounds good.
Think of this as like your direct line to understanding a concept that's shaping a lot of what's happening in tech right now.
Exactly. And at its core, task agnostic. It describes systems that aren't built for just one specific job. It's really about generality.
Generality, okay.
Yeah, the ability to handle a wide variety of tasks without needing a complete overhaul for each new challenge. It's fundamentally about being adaptable.
Right. So instead of a tool that does one very specific thing, like a screwdriver, it's more like, I don't know, a multi-tool,
Yeah.
something that can turn its hand to many different things.
That's a good analogy. These systems thrive on that flexibility, being able to shift gears when the task changes or, when you're faced with just a really diverse set of problems.
Right.
And what's truly interesting, I think, is that this flexibility often comes from quite fundamental methods.
Oh,
It's like having a core set of problem-solving skills you can apply across different situations, rather than, say, a rigid instruction manual for every single scenario. Learning algorithms are a perfect illustration here.
how so?
Well, they can learn from varied data and then apply that learning to tackle a wide range of problems.
That makes complete sense. Now, to really bring this home for everyone listening, maybe some concrete examples right off the bat.
Good idea.
Think about, say, programming languages, Python or Java, for instance.
Mhm.
They weren't created just to build websites or just for data analysis, right?
Not at all. You can use them for a vast spectrum of software development tasks. That's task agnosticism right there in the coding world.
The same foundational tools applied to wildly different problems.
Precisely. And if we look at artificial intelligence, AI, deep learning models like transformer architectures are a prime example then.
Transformer, right. Huge topic.
Absolutely. Initially designed for understanding language, these models have shown just remarkable versatility. They handle tasks from translating languages to categorizing text and even answering questions.
Seemingly very direct linguistic challenges.
Exactly, all tackled with a similar underlying design. It's quite something.
It's almost like they've developed some kind of fundamental grasp of language that they can then apply in various ways.
Sort of, yeah. And on a more maybe conceptual level, you could consider cognitive architectures, things like SR and ACTR.
Okay, those are a bit more academic.
A bit, yes. They're frameworks that try to model how the human mind works, and they can then be used to simulate all sorts of different cognitive processes, making decisions, solving intricate puzzles, that kind of thing.
Interesting. And I guess the key thing to understand here is how they differ from the opposite approach.
Right, the contrast with task-specific systems really helps clarify. Think about a highly specialized robot arm on a factory assembly line. It might be designed to perform one very particular welding operation, and essentially, well, nothing else. Task-agnostic systems are just designed with a much broader scope in mind from the outset.
Okay, so we're getting a clear picture now of what these systems are, but why is this approach, gaining so much traction? What are the real advantages here?
Well, flexibility is a big one.
Right, applying them to lots of different problems.
And adaptability, the potential to learn new things without starting completely from scratch every time.
Uh-huh. And reusability, I suppose, using the same core system in multiple contexts.
Absolutely. If you connect this to the bigger picture, just imagine the gains in efficiency if you don't need to engineer a completely new solution for every single problem you encounter.
Yeah, that makes sense.
That ability to reuse fundamental components can lead to, well, significant savings in development time and resources.
But it can't be all sunshine and roses, can it? There must be some trade-offs involved. You mentioned challenges earlier.
That's right, there definitely are. A primary concern is that a general purpose system might not achieve the absolute peak performance on a highly specific task.
Compared to something custom built for just that one thing.
Exactly. It's that classic trade-off, isn't it? Breadth versus depth. And to achieve this wide-ranging capability, the underlying mechanisms often need to be quite sophisticated. That can lead to increased complexity.
Okay, makes sense. Complexity and maybe slightly less peak performance on narrow tasks. Let's dig a little deeper into this then. We have a solid handle on the what, maybe explore the why they matter more, and how they work under the hood as we continue.
Agreed. This initial overview gives us a strong base to build on.
Now let's shift our focus specifically to how this whole concept of task-agnostic systems is, Well, showing up in artificial intelligence. It really feels like this is where some of the most exciting stuff is happening.
Absolutely. In AI, I think the push towards task agnosticism is driven by this ambition to create more generally intelligent and adaptable
More
systems.
general intelligence.
Yeah, imagine AI models that aren't just, say, experts at one narrow thing, like identifying cats in photos,
Right.
but can also understand human language, interpret complex visual scenes, maybe even control robots, all stemming from a broad underlying understanding of the world, or at least the data they've seen.
It's like moving from having, I don't know, a whole toolbox of highly specialized wrenches, each for one specific bolt size, to maybe having a few really good adjustable wrenches that can handle a much wider range of jobs.
That's a great way to put it. These AI models, when they're trained on a really diverse array of tasks and information, they start to build a much more holistic kind of understanding.
Uh-huh.
And this inherent flexibility becomes incredibly valuable in dynamic fields, like natural language processing, where language is constantly evolving, or computer vision, where the variety of visual inputs is just endless. And even robotics, where a single robot might need to perform many different actions in unpredictable environments.
Right, adapting on the fly.
Exactly. And this is where some truly groundbreaking AI models come into the picture. You mentioned transformers earlier.
Yeah, the attention is all you need.
Yeah.
Paper, right? That really kicked things off.
It really did. It established the groundwork for their ability to handle a multitude of language-based tasks. The core idea, this attention mechanism, basically allows the model to focus on the most relevant parts of the input data.
So it learns what's important in the context.
Precisely, which makes it remarkably adaptable for things like translation, text classification, even something as nuanced as answering questions based on a given text. It's essentially one fundamental architecture
Okay.
that can be fine-tuned for a surprisingly diverse set of linguistic challenges because it learns to weigh the importance of different words in a sequence, which is, a pretty fundamental aspect of understanding language in general.
It's almost astonishing how one core design principle can be adapted so broadly within language. So what about other types? We hear about GANs a lot, generative adversarial networks. How do they fit in?
GNs. Well, what's particularly insightful with GANs in this context is their ability to learn the underlying patterns and structure of data
Okay.
and then generate new samples that resemble it. They aren't really about solving a specific classification or prediction problem in the way we usually think about it.
So they're not labeling things, they're creating things.
Exactly. They learn a general process of creation, you could say, and this allows them to be applied to a wide spectrum of, well, creative tasks, generating photorealistic images.
We've all seen those examples.
Right, or expanding existing data sets, data augmentation, even transferring the artistic style from one image to another. The core task isn't fixed. It's about learning this flexible generative capability by understanding the data's statistical distribution.
So they learn the sort of underlying rules of the data and then can apply that learning to create new things, maybe in different domains or styles. That's a really fascinating angle on task agnosticism. It's not just about doing different tasks, but creating in different ways.
Well put. And then, sort of related, we have the concept of meta-learning models. MAML is a key example
I
there.
have a learning.
Yeah.
Learning how to learn, that sounds particularly intriguing.
Exactly. That's the core idea. Meta-learning models aim to learn good starting points or effective learning strategies
Right.
that let them quickly adapt to new, previously unseen tasks using only a small amount of new data.
So it's about efficiency in learning new things.
Yes. Instead of learning each task completely from scratch, they learn a general approach to learning. So if you train a meta-learning model on, say, a variety of different image classification tasks, it can then rapidly learn to classify completely new types of objects with just a few examples. It really highlights efficiency and the ability to generalize the learning process itself.
So these models aren't just learning to perform specific tasks, they're learning the fundamental process of adapting to new tasks efficiently. That feels like a significant leap towards truly versatile AI, doesn't it?
It really does.
And just like with the broader concept we discussed earlier, these AI models, they come with both significant promise and their own set of challenges.
Right.
It's not all figured out yet.
Absolutely not. The potential benefits in the AI realm are Well, enormous. We're looking at AI that's not only more flexible, tackling a wider array of problems,
Mhm.
but also more efficient potentially because you might not need to train a massive model from the ground up for every single new application.
Less retraining time and cost.
Exactly. And the enhanced creativity aspect, particularly with models like Jan's, opens up entirely new avenues for generating novel solutions, new ideas, new designs.
That sounds incredibly promising for, well, a vast range of applications, from science to art to engineering. You mentioned challenges. What are some of the specific hurdles in actually building and deploying these powerful task-agnostic AI models effectively?
Well, one major challenge, and it's a practical one, is just the sheer computational resources required.
The cost of training them.
Yes. Training these large general-purpose models on vast and diverse data sets demands significant processing power, GPUs, TPUs, and time. It's expensive.
Okay, what else?
There's also the heightened risk of overfitting.
Ah, right, where it learns the training data too well.
Precisely. The model becomes excessively specialized to the quirks and nuances of the specific data it was trained on, and then it fails to generalize effectively to new, unseen tasks or slightly different real-world environments.
So it works great in the lab, but not so much out in the wild.
That can happen, yes. It's a delicate balancing act, learning enough general patterns to be useful without just memorizing the training data itself.
That makes sense. You're building a system to handle many things, so naturally it needs to learn a lot, which takes resources. And the more complex it gets, the greater the risk of it becoming too focused on the training specifics. But I know there's a lot of ongoing research aimed at tackling these exact issues, isn't there?
Oh, definitely. Researchers are actively developing and refining various techniques to mitigate these challenges, regularization techniques, for example.
Like dropout.
Exactly. Dropout, weight decay, early stopping. These are all crucial for preventing overfitting. They essentially add constraints during the learning process, encouraging the model to learn more generalizable features rather than relying on specific data points.
So kind of forcing it to learn broader rules,
In a way, yes. Then there's data augmentation.
making more training data.
Artificially, yes. You increase the diversity of the training data through transformations like rotating images, scaling them, flipping them horizontally.
Okay.
This helps the model generalize better because it's exposed to a wider range of variations during training. It learns to ignore irrelevant changes.
Makes it more robust to slight differences,
Right? And another huge one is transfer learning.
using pre-trained models.
Yes, leveraging knowledge learned from models already trained on massive data sets, often by large companies or research labs, and applying that knowledge to new related tasks. This can significantly accelerate training for your specific need and improve performance, reducing the need to start from absolute scratch every time.
So it's really a multifaceted approach, isn't it? Focusing on making the models themselves more robust, the training data more comprehensive and varied, and the whole learning process more efficient by building on previous work.
Exactly. It really sounds like there's a strong, concerted push to unlock the full potential of task-agnostic AI.
Agreed. The ultimate goal is to really capitalize on those advantages, the versatility, the efficiency, the creativity that these models offer,
Yeah.
while developing effective strategies to manage the inherent complexities and the computational demands.
And if we can continue to make progress in these areas, and the progress has been rapid,
It certainly seems that way.
then we can anticipate a future where AI can be applied to an even broader and more diverse spectrum of tasks, with greater adaptability and hopefully less reliance on highly specialized, task-specific engineering for every little problem.
This has been a truly illuminating deep dive into the world of task-agnostic systems, particularly, as you say, within the context of AI. It's clear that this approach holds, well, tremendous promise for creating more flexible, more efficient, and maybe even more imaginative technologies down the line.
Agreed. It feels like a trajectory that has the potential to fundamentally change how we even conceive of and develop intelligent systems in the first place.
Definitely food for thought. Now, for a final thought for our listeners to consider. Given the potential for these adaptable AI systems to become increasingly prevalent across all sorts of industries, really think about the sectors you're most familiar with, your job, your hobbies, your interests. What entirely new possibilities, maybe things we haven't even conceived of yet, might emerge as these technologies continue to evolve and become more deeply integrated into our world? It's a question that could spark some truly fascinating ideas about what's next. Thanks for joining us on this deep dive.